Thanks everybody for being here on a Friday morning as the semester's ramping up. It's my pleasure to introduce Professor Greg Stein. We've known each other for several minutes now, but we have a close collaborator in common, which is Shui-Su Zhao, who used to be a postdoc here. Many of you know him. He's now faculty at George Mason with Greg, and Greg comes to us. He did his PhD at MIT. Prior to that, he was at Cornell. His talk has a title that I'm not going to read to you because you can read it.
Yeah, no, I'm not going to read it either.
Okay, right there. But he does run the Robotic Anticipatory Intelligence and Learning, or RAIL group at George Mason, and his research is at the intersection of robotics planning and machine learning. It's centered around developing representations for planning and learning that allow robots to better understand the impact of their actions so that they may plan quickly, intelligently, and reliably in a dynamic and uncertain world.
Great.
Thanks for that in the bio.
Thanks so much. Yeah.
Just schedule-wise, we have a sign-up schedule. There's still some spots, so if anybody wants to jump onto it. Right now, Ray and I are scheduled to take him to lunch, but if anybody wants to jump in on that, I might then switch to taking him to dinner. So there's still flexibility in the schedule. And I'll just say our next Forum for AI Talk is in 2 weeks. Gaurav Sukhatme from USC, a star roboticist in the field, will be here. So put that on your calendars as well. So really great.
I would like to reiterate the thanks for everyone being here between the ICRA and iClear deadlines. I'm feeling that pressure as well, so I appreciate all of that. But yeah, so I'm Professor Greg Stein. I work a lot on planning, and I think about the interface between planning and learning a lot. And I think, like many of you, I'm really interested in this general vision, the idea that robots are going to be expected to enter our homes, to enter, buildings, hospitals, offices, etc., and complete a variety of tasks. Everything that goes from the relatively mundane, things like, rearrangement, object manipulation, like telling the robot to load all these objects into a cabinet, to the slightly more complicated scenarios where a robot might be expected to prepare breakfast, or the more sequential make the bed and restock the shelves and then bring breakfast. All of these things require that the robot interact with many different objects in the environment. There's some 50 years of planning from Shaky the robot all the way up till now that says that we can write these down in various different ways. One of my personal favorite tools to use is something like PDDL, or the Planning Domain Definition Language, which can be very useful for writing down the sorts of things that the robot can do to change the state of the environment, and the tasks, which we write down as a union of predicates. Now, I think many of you may have seen Lisp or Lisp-like languages, but this goal that sort of corresponds to this more natural language instruction, load these objects to the cabinet, says that we just have some union of red block number 1 is in the cabinet, the first red block is in the cabinet, all the way down to the final blue block being in the cabinet. And if we give the robot some set of high-level actions, skills that the robot can execute to transform the state of the world, then we might be able to sequence those together. And indeed, the objective of a planner is to come up with a sequence of these actions that transforms the state from the initial condition into some state in which the goal is satisfied. So we might have some actions where the robot moves to the table, it picks up blue block number 2, it moves back to the cabinet, and so on and so forth until the plan is completed. Now, there's a lot of work in the space of task planning and many well-established approaches to solve them. But I'm really interested in this maybe more specific, but I would argue maybe also more general formulation in which the robot may not actually know everything about the state of the world. And in particular, I'm really interested in this domain where robots are going to be able to, or going to be expected to, not necessarily able to, complete these complex objectives despite significant and pervasive uncertainty. The idea that the robot may not have a map of the environment and so must search for many task-relevant objects. It may not even know the set of objects that exist and so must consult some sort of prior knowledge in some way in order to be able to fill in these missing pieces. And suddenly these scenarios that I showed earlier become quite a lot more complicated, because in addition to having to figure out exactly how the robot is going to do some high-level task like prepare breakfast, for which it may have multiple different pathways. It could, make cereal by finding milk and pouring it into the bowl. It could make yogurt. It could serve fruit, it could serve eggs, many different ways to complete this task. The robot now also has to reason about what objects might exist in the world and locate them along the way to trying to complete this objective. It's a very difficult task, one that, I'm going to try and motivate why it's so hard and then talk about our solution strategies. But I'll remind everybody that this is a very pervasive strategy. Planning under uncertainty is something that you do almost every day. I've navigated multiple buildings that I've never been in before today, moderately successfully. But for the most part, there's like a lot of different ways in which objects move around or are not available to you or known to you, and yet humans have a remarkable capacity to make progress towards these objectives, informed by their experience, despite all of this missing knowledge. So to motivate how hard and why this problem is so hard, I'd like to go to that navigation in unfamiliar buildings example. This idea that navigation under uncertainty is a great exemplar task for illustrating why planning under uncertainty is so difficult. So imagine a point-goal navigation task. You have some ground-based vehicle that's told to get to some objective that's roughly 100 meters out and to the left. How should the robot get there? Well, if the map is known, the navigation problem is relatively straightforward. You have a map, you have some occupancy grid or whatever your map representation is. You can run your favorite motion planning algorithm and then plot a dynamically feasible trajectory that goes down the hall, makes a left at the bend, and then continues on to the goal. But the planning under uncertainty problem says, well, what happens if I can only see what's around me? Maybe the robot is capable of building a map with some high level of reliability, but even then the robot must make decisions about how it's going to plan when it leaves known space and enters this unseen part of the world. A sort of simple but popular and reasonably effective strategy in this domain is what I will refer to as optimistic planning. The robot optimistically assumes that all unseen space is unoccupied, and the absence of any interfering structure means that the robot makes an early left turn into this space over here. Now, as you can see from this video of this robot entering this area, this is a classroom. And like many classrooms and meeting rooms, with the exception of maybe the occasional emergency exit, this is a dead end. So the robot, not knowing it's a dead end, enters that part of the environment and explores the entire space before realizing it's a dead end and has to turn back. And the problem with this is that optimistic planning in general begets suboptimal behaviors. The plan that was generated by this robot was this one that we show over here. In this simulated large-scale environment, the robot is trying to find a route around the hallway and tries along the way to enter many classrooms and offices and closets, places that humans would not enter because we understand the value of a hallway to connect faraway regions of space. In fact, that's arguably the reason of corridors and hallways. But we actually understand, based on what we can see in our local part of the world, the types of things that might exist in the world nearby, and even farther than that, more long horizon decisions that are very difficult to reason about if you're thinking like this. If you're just making these optimistic assumptions, you can make progress towards completing your task and then revise your plan as the environment is revealed, but this generally leads to fairly poor behavior in general. So let's go back to this task planning domain. What does this notion of optimism under uncertainty look like when you're starting to think about these more complicated tasks? Well, there's a relatively simple strategy, one that I most recently, my collaborator George Kandadaris at Brown University has formalized as a LOMDP, a locally observable Markov decision process, which sort of codifies this idea in some mathematical formulation, basically saying, as I reveal the world, I know it with a very high degree of reliability, and the goal is to expand what George and now I are starting to call this envelope of observability, within which you know the state of the world, and the goal is to keep exploring nearby, revealing as much of the world as you need until eventually you have enough objects or you know enough stuff that you can complete the plan using classical planning strategies, using known space planning based on what you've seen. This is a great approach in many ways because it's simple, it's sound and complete. You're just exploring nearby, and it's flexible and portable for new tasks. It has all the hallmarks of things you might want from a planner. As you give the robot new objectives and things like this, eventually you will reveal all of the world and can complete the task or tell yourself, no, I can't complete this task because I've looked everywhere and haven't found the things that I need. The cons are, of course, very similar to the ones that we saw in the navigation case, which is arbitrarily poor performance. The robot isn't particularly intelligently or effectively looking in its nearby vicinity. It doesn't really yet understand even what objects it may need to find or which objects it should prioritize looking for in order to complete its objective. And so the robot ends up just kind of ambling about until it gets lucky. And that's not great because we would like to think that we should do better than getting lucky in these really complicated, demanding environments, especially when performance could be of the essence. And so we can get almost arbitrarily poor performance. The challenge here in overcoming this limitation is that there's not a straightforward way to fill in missing knowledge. And so planning is mostly uninformed. Now, the solution to this, especially since I know many of you here work in the space of planning and learning and think about the ways that learning can make predictions about what lies in unseen space. And indeed, you might be able to find some way to use a learned model or more recently, foundation models and language models and ChatGPT, the foundation models being an umbrella term for everything that you might use that isn't just classical planning, to help guide the robot towards good behavior. So with this in mind, let's look at kind of the other side of things. Rather than thinking about how we might solve this by taking planning tools and sort of making assumptions or approximations to try and use what we already knew how to do for 50 years to tackle this problem, let's look at something that really doesn't do any of that. Let's look at something like SACAN, and this is not the most modern approach, but it's an approach that I think is a really good exemplar of how one can intelligently and effectively use a language model or some other predictive models to decide what the robot should do next. The way that SACAN generally works is it basically says, I'm going to try and propose some reasonable next actions based on the language model, and then based on that proposed candidate set of actions, pick the next action that is both a reasonable thing to do and likely to be accomplishable. So it also has some affordance model that's making a prediction about whether or not that action can be successfully completed in this environment. And between the two of those things, this ends up being a relatively, a very powerful and fairly flexible way to tackle these sorts of open-ended tasks described in natural language, and it performs fairly well in practice, where the caveat is that fairly well is something like 60 to 80% success rate. So different sort of assumptions, different sort of domain. But the cons, of course, are that it's not complete in general, right? You're not actually really writing down explicitly all the things that the robot can do. So the generality comes at the expense of being able to actually successfully complete all of your tasks. But the one thing that I want to point out as well is that there's no notion of performance or cost in this. The robot is always trying to relatively greedily pick the action that it thinks is best, albeit with a very powerful heuristic. The learned model is trying to tell you how to pick actions that seem like the best, but without any sort of deliberate forward-thinking reasoning, unless the next action is fairly obvious, which it is in a relatively large number of cases. It can be very difficult to decide which of the possible candidate actions are most effective for making progress towards this task. And so SACAN is ultimately greedy with this powerful heuristic. And so it's well suited to pick the most reasonable actions, but not necessarily best when we want to actually perform well or come up with efficient or low expected cost solutions. The challenge in something inherent like this breakfast preparation task and others like it is that good behavior depends on many factors, including what objects exist and the ease with which we can find them. Effective behavior in these sorts of planning under uncertainty domains requires nuanced, long horizon reasoning to yield plans that jointly search, interact with various objects, and when necessary, gather task-relevant knowledge about the environment. So LLMs and other sort of learning-based models can do a pretty good job at solving some of the relatively easy problems from a planning perspective. They can generate reasonable candidate next actions, but can be somewhat unreliable and in particular myopic for long horizon task planning. So just as large language models are somewhat notoriously poor at math and numerical reasoning, we shouldn't necessarily expect that they're going to be good at a lot of these planning tasks for which finding the best thing requires a lot of mathematical operations. They aren't well suited to make good judgments about what actions are lowest expected cost in these complicated and open-ended tasks with many potential solutions. So the idea and the thing that I'm going to be talking about for the rest of today is this notion of learning augmented planning. That within my lab, a lot of my work tries to find the balance, the strengths of both planning and learning in these domains. Planning, because it is designed for effective and reliable long horizon decision making, you get nice properties. It's sound, complete, portable, general. It's extensible in many ways. You can add new actions to the robots as you find new capabilities and introduce new actions into the environment or new objects into the environment. But you still need some elements of learning to help you reason about uncertainty and just missing knowledge more broadly. The challenge, though, is that it's not necessarily clear how to accomplish something like this. Existing task planning tools typically presume full access to the environment, to the state of the world, and so are not straightforwardly applicable in this domain. We need new models, abstractions aimed at bridging this gap. And this is one of the central aims of my lab, to develop a novel family of abstractions that facilitate the integration of learning to augment otherwise classical planning. State and action abstractions provide reliability, flexibility, and portability by determining, and by writing down the ways in which we can interact with the world. But then learned models provide statistics about uncertainty. They tell us more about the missing or hidden knowledge that we need in order to be able to then inform effective behavior. With this in mind, let's revisit this point goal navigation task. Looked at from above, we can simplify this scenario in this little toy scenario over here. We have the robot in known space and it's trying to get to the goal and it has multiple different ways that it can try and traverse to try and sort of leave known space and enter the unknown in order to find the goal. In this space, and we're not the only people to do this. I know, like Christian Grauman's lab does a lot of like frontier-based action definitions and things like that here. And, and a lot of people have done this, but we define exploratory actions that each correspond to exploration beyond some subgoal, some point on the frontiers, a boundary between free and unknown space through which the robot can traverse and then try and find a route to the unseen goal in unseen space. So this is our action abstraction. This says in general, here are the ways that the robot can leave known space to try and make progress towards completing the task. But in addition, I'm really interested in using this for planning. And so we don't need to think just about the things that the robot can do, but the outcomes associated with doing those things. And so this abstraction incorporates not just here's the different actions that the robot can take, but also the sorts of high-level outcomes that can happen when the robot navigates through each one of these boundaries. And to simplify this a little bit, actually quite a lot, rather than reasoning about specifically the structure of each one of these parts of the environment, we ask a topological question. What is the likelihood that there exists a feasible path to the goal if I were to go through this boundary? And that alone is a relatively simple question to ask. We can train some learned algorithm to predict the probability based on some supervised learning in similar environments and similar sets of training data pairs. And based on this action abstraction, this outcome, or these sorts of outcomes, we can instantiate a model. And so when you have a model, when you think about planning, you should think of the Bellman equation. If you don't, we should talk because you need to think about the Bellman equation more. But given this abstraction, we can now estimate or try and compute directly the expected cost associated with executing any of these actions. So here's an example of this. I want to know what is the expected cost of executing action number 1, where that corresponds to traversal beyond this boundary over here on the left. Now, the first thing the robot does upon choosing this action is navigate to that boundary. Now, as I mentioned before, that's movement through known space. I know how to do that. I get some task planner, I get some motion planner that can plot some trajectory that goes to that boundary. But then the robot accumulates some cost of traversal through known space. But upon getting to this boundary, our high-level action abstraction says that one of 2 outcomes is possible. With some probability, the robot succeeds in reaching the goal and accumulates some expected cost of success. And with the inverse probability, it fails. It has to navigate this classroom or whatever it is, realize it's a dead end, and then be forced back to try and find an alternate route to the goal. And then in the event that we do not succeed at completing the task, we're not done, and this process continues recursively. The problem implicit in this equation over here is trying to find the sequence of exploratory actions that will be most effective to minimize expected cost for traversing this environment. And so you might be wondering now, how do we get some of these terms? This probability of success or failure, the expected costs of success and exploration are all things that we don't have direct access to. So instead, we use a learned model to estimate those things, trained via supervised learning. And as a result, we refer to this as our learning over subgoals planning abstraction. It is a high-level action and outcome, or like some high-level abstraction for planning that mixes planning with the input from learning. So learning is used to help instantiate a model that we can then use to make long horizon decisions, despite this significant long horizon uncertainty.
Can I ask?
Yes.
So this model that you're learning about costs is specific to this robot.
It is specific to this robot. And I have another paper that actually, the embodiment of the robot is actually an input parameter as well.
Okay.
So, right, you can think about this as well, but yes, exactly.
So an approach that I would kind of consider a first attempt is learn a distribution over maps.
Yeah.
Right, and then use some sort of Monte Carlo research to choose an action that works in most maps or whatever.
Yeah, absolutely. I think that's a great solution when you're planning only about like 15 to 20 seconds in advance or something like that. But beyond that, when you start thinking about navigation or task planning over many minutes, it can be very difficult to reason far enough in the future that information is still valuable. Again, the sort of simplifying assumption here is one that we can make predictions about the topological class of the distribution over topology of the unknown environments. And then by estimating that statistic, we could do a much better job of compactly reasoning about how good it is to go in a particular direction. But yeah, there's a lot of work I've seen that does some map prediction. I just don't think it extends to sort of like long horizon scenarios like this. Yeah.
And this is all in the setting where you're planning towards a goal and that's all you care about. So,
right.
So because there are other reasons to go explore in the places that have
Yeah.
low probability of success, because they might be useful for your future planning.
Right.
But here, you're completely, this is like, the world ends once you get to the goal.
The world ends once we get to the goal, but I also, so first of all, we're building to something. And so later on, I'm going to talk about the more complicated scenarios that build on this idea. So think more about task planning and expected information gain and things like that. But I also want to point out that sometimes the robot will indeed, there's benefit in doing this sequential, this expanding the things that might happen and what I might do as a result. Even in the scenario where the goal is just the terminal state and the world ends when I'm done, there's still sometimes value in peeking in places that I think are low likelihood, but have enough expected value that I should still look inside them. So the robot is still going out of its way to do things that are lower likelihood sometimes because they're on the way and there's a high enough probability or some potential for a shortcut that still makes that action the best action to execute.
Sure, but that's only because it's a potential to have a shortcut for this goal. There's nothing.
Correct. This is
do
the
with it.
world ends after this. Absolutely, yeah, correct. So the planning loop with this is relatively straightforward, but the thing that I want to reemphasize here is we're not just picking that action, then we're executing it fully. As the map is updated, the set of possible things we can do changes. We're given more information. And so as we go, as the robot reveals more of the world, we're constantly redoing this high-level planning because our model is approximate. So we're sort of sweeping under the rug a lot of the details about what might lie in unseen space. As we continue to map more of the environment, we see more stuff and can then do a better job of saying what actions we have and places to go, etc. Informed by this learning augmented or this learning informed long horizon planning under uncertainty strategy, our robot is capable of understanding that some of these things like classrooms and hallways, despite looking attractive from this myopic optimistic assumption, are not the best way to get to this unseen goal, and as a result tends to avoid these sorts of regions in the environment until it gets close enough to the goal that they seem like productive behavior. And the same thing is true in this simulated environment as well, where we can see that the robot does a very good job of generally sticking to hallways without being told what a hallway is, because it recognizes the geometric features associated with this hallway and can do a much better job of knowing what is the most effective way to go to make progress towards this long horizon objective. So this learning over sub-goals planning abstraction has some really nice properties. Planning is sound and complete, and executing an exploratory action will reveal space and so on and so forth until the environment is fully revealed. And in particular, learning is only used to make predictions about uncertainty. When the world is fully known, and within parts of the world that are fully known, learning is not used because it is not needed. The key idea, what makes a lot of this work, and then I'm going to be building on for a lot of the rest of the talk, is this idea of learning augmented model-based planning, that learning is used to estimate parameters of a family of models, but planning itself is classical, and so done without reliance on learning. So you might also be thinking, well, how did you actually do this learning? And I've intentionally kept that vague because we have a number of different projects that, while not specifically the point, use different learning modalities as history has progressed over the last however many years since I've been doing this, where we went from predicting geometry from structural features to using convolutional neural nets, graph neural networks, and even now language models where we describe the environment to the robot. And we're trying to say, hey, if I go this way, what does that look like? And we can get captioning models to tell us it's a classroom and all that stuff. There's lots of different ways that you can predict these statistics. And actually, one of the things that has really been an upshot for us for development with these models is that the abstraction itself just says you have these estimators. And wherever those estimators for the statistics of uncertainty come from, you can swap them out as long as they are still effective and use the same action abstraction, where the predictor that tells you what uncertainty looks like or what you're likely to encounter when you leave known space can be replaced with whatever more domain appropriate model is. So that's been a really nice benefit of this particular approach. So now moving forwards a little bit, and some work that was done in particular with collaboration with Nick Roy, my PhD advisor, and also Hadas Kresge at Cornell, was now asking ourselves, well, how do we then extend this to also think about task planning? And based on, of course, this wasn't obvious at the time, but with the benefit of hindsight, we can now think about this as just actions being things that help us advance the state of the plan, where we can have this set of exploratory actions that each correspond with ways to reveal some of unknown space or some missing knowledge strategically, where the costs and outcome probabilities are estimated via some learned model, while the robot also has some standard known space actions that, as the world is revealed, the robot can then interact with the objects that the robot has already observed. And so between the two of these things, we now have a number of different ways that the robot can either make progress in known space or continue to strategically expand its envelope of observability to make progress towards revealing the things it needs to then actually complete the task. So we have this, a bit of a disclaimer. This is like jumping ahead in time to some work that is actually currently ongoing with my collaborator George at Brown University, but it's the same underlying family of abstractions. So I'm going to talk about it because I think the results are a little bit easier to parse. But the setting here now is that we want to have a robot that retrieves 3 objects in some environment that's never been in before. It has a partial map. So we have something that looks like this is the Proctor environment. They're procedurally generated homes provided by the Allen Institute, where the robot can now, look around in various different containers throughout the environment. There's tables and cabinets and countertops and things. The robot generally knows what rooms exist and where the cabinets are, but it doesn't know where any of the objects are. And so it must look for them. Now, this here, despite the plan looking actually quite poor, is what happens when we use a very good learned baseline for this task. The robot is using learning to find each one of these objects. So there's lots of different work and some really good work that says, I'm going to have some object search pipeline. I'm going to take, I'm going to have a robot embodied in this environment, and I'm going to look for object number 1. And then when I find object number 1, I'm going to look for object number 2, and then so on. But unfortunately, because the high-level planner has no notion of which object the robot should look for first, or how to search the environment more strategically to try and look for places where multiple objects might exist, this actually ends up doing a lot of backtracking, because while looking for object number 1, the robot might have had an opportunity to find object number 2, and so on and so forth. And so the sequencing of this exploration is actually really important. Our approach doesn't need to do that. We don't look for one object at a time, or we don't necessarily need to look for one object at a time. We're able to much more effectively search near us to find the objects that we might need. And as a result, our trajectory here is much more efficient, looking for objects as we traverse in an effort to minimize total cost to complete the objective. And again, the thing that really makes this possible is this high-level action abstraction. We're not just trying to do the thing we think is best more myopically. We're trying to globally solve this objective as effectively as possible. We can also revisit this breakfast preparation scenario where, in the language of this is kind of approximatized PDDL, we could say that we need a boiled egg, or a boiled egg in a bowl, or some toast on a plate, which means that along the way I need to either find the toaster or a pot and fill it with water to boil. And there's like 16 different objects that you might need to interact with. And which one of these solutions you do, whether you try to boil the egg or toast the bread, depends on how likely you think you are to be able to find a toaster or the eggs, and how effectively you think you can find them. So it's a very complicated reasoning problem in order to try and solve this. But our plans interleave search and execution. The robot is constantly balancing, looking for things that it might need, while also making progress towards the task along the way. A hallmark of good behavior in these domains that is not exhibited by these more myopic strategies that explore and then act.
So if I was a robot and I was only trying to maximize the probability of achieving the goal, right?
Yes.
Then I would pick up an egg, and then I would pick up a piece of bread.
Yes.
And then one of them would go to waste, right?
Right, exactly. So we're not taking that into account. Food waste is important, but that's not in this work. I think, it's another way of thinking about, the sort of positive and negative benefits associated with each one of these actions. It's not in these experiments, but I think it would be relatively simple to incorporate some stuff like that. This is actually a thing that Hadas Kreskazit has complained about before, because she thinks a lot about, verifiable planning and safety. When you plan under uncertainty, you may cross a threshold that later you discover you can't go back from it. So it's very difficult to use some approximate, very high level abstraction in that domain. And I don't know how to straightforwardly solve that problem. But yeah, very, very good point. So cool robot demo time. We also showed some of this stuff on a spot robot, and I'm very happy with this. This is, we just got these like 3 days ago. But it's the same sort of thing. We give a robot a very high level objective, and we show that compared to any of the other baselines that don't necessarily think about this long horizon planning problem, they're incapable of getting the sort of like balancing, exploring, and executing the plan behavior that our planner is capable of achieving. So I'm gonna, just a little lightning tour, because I'm a little over the time that I want to be right now, is we've used this same general abstraction for lots of different planning problems. We've done things like coverage, maximizing exploration. Don't stare at the video too hard, it's a little dizzying, but this is a robot moving through these environments, trying to map as much of it as possible in some finite amount of time. We've also done this for some active information gathering experiment. I don't know about you, but when I enter a new building I've never been in before, and I truly have no idea which way to go, I go to an elevator bay and look at the map, because there's almost always some fire safety map that says what the layout of the building is. This is the sort of behavior we incentivized in this robot. It's a very difficult thing to do, because the robot has to expect, in expectation, understand the value of going out of its way to look for a map so that it can then benefit from having had a map. So it's a very, complicated long horizon reasoning problem. We use our abstraction to try and estimate this expected value of information. And that was a really cool project. And, I'm happy to talk about it more offline if people are interested. And then more recently, a lot of the things that I've been very interested in are doing some things that are really difficult to do in this more, in the absence of model-based planning. And one of the ones that I've been thinking about a lot is this multi-robot coordination, where we show this. It's much easier said than done. And when we started this project, we said, oh, we'll just take the abstraction, we'll do it with multiple robots. That was like 4 years ago. And so very hard to then translate a lot of these problems to these multi-robot settings because there's a lot of bookkeeping involved. And we had to invent some really cool approaches to handle this complicated state transition model where the robots are simultaneously executing actions that have non-uniform durations with many different possible stochastic outcomes. Very cool project. Please see our paper for details. I'm really excited about some of that stuff. And the most recent thing tries to take a centrally coordinated team of robots and then apply this to this long horizon task planning under uncertainty domain, where we're simplifying things a little bit. The robot team is homogeneous. They never work together on any actions, but each robot can individually make progress towards either revealing some part of the environment or picking up the egg or the toast, etc., the bread to be toasted in different parts of the environment. So we can take our action abstraction that was effective for single robots, and again, with the magic of a lot of bookkeeping and some clever code, we're able to track where we think each robot is going to be as a function of time, and then use that in order to try and come up with some long horizon behavior for how the robot team should explore the different parts of the environment. And so this has been some ongoing work. I'm really excited to share this if people are interested in this. Again, I'm happy to talk about it more offline. But the thing that really makes this possible is this high-level abstraction, where rather than thinking about specifically what we might counter in every single part of the environment, we're now thinking a little bit more abstractly about how we might reveal space, how each one of those things has a potential to make progress towards the overall objective, using learning to make predictions about how long those things are going to take and how expensive they're going to be. And so some more recent progress, and this is some demo. This is one of my grad students' apartments, where we have a couple different turtlebot, like locobot robots that are moving around the environment, trying to find a number of different objects in that space. And the sort of naive behavior to tell the robots, yeah, split up, but search containers nearby is not very effective. But ours does a very good job of understanding how the robot should kind of divide and conquer the different parts of the environments to strategically make progress simultaneously. And so again, this is really a hallmark of good behavior in these domains. And some of the more recent stuff that we've been doing has been trying to think about how this works for, more hierarchical planning. Take a large team, split it into subteams that now have differential capability and can each then accomplish different parts of the plan. So a lot of it relies on this underlying model that we have been working on and iterating on for quite a long time. But I'm very excited to see how this work is progressing.
And they're all communicating all the time.
Centrally coordinated, yeah, fully centrally coordinated. The sort of as soon, yeah, I'm really interested in the missing information problem, but that has proven a black hole for 2 grad students. It's really, really hard when communication drops out, but I'm very interested in it. So far, and this is, I think when you start to think about deploying these learned systems, I think one of the things that everybody who actually works with these systems thinks about is, well, what does it look like when I actually start to deploy these things? What do my deployment time environment look like? And so far, we've assumed, like many people that work with learning, that the training and test environments are somehow similar to one another. So that's great. If I train in environments that look a lot like my deployment environments, I should expect my performance to be pretty good. My predictive model about what lies in unseen space is going to be relatively accurate, and that's good enough to inform pretty good behavior in these domains. But as soon as I deploy my systems in some environment that's fundamentally dissimilar in some way that is difficult to write down from my training environments, I can have almost arbitrarily bad behavior. Now, again, we are sound and complete, so eventually the robot will make its progress to the goal, but this is not fantastic. The robot does a really bad job. And even in the absence of other data in these environments, you can see that the robot did a bad job. Now, so far, we've focused a lot on this idea that our abstractions let us act in our predictions. We make some predictions about what lies in unseen space. We use that to create some model for the purposes of planning, and then we can use that to tell us what to do. But I'm really interested in going back in the other direction, this idea that our experience should also inform our predictions. So this is something that there's some work in the space of like runtime monitoring and introspection that I'm really interested about. But it's really interested in, but it's very difficult in this long horizon planning under uncertainty domain because we have a really difficult time connecting any one of our predictions to the actions that the robot made. So it could be very difficult to deploy a robot in one of these systems and to look at the robot and say, yeah, that was bad, you should improve. Now, the idea that we're building on here is, again, taking advantage of the fact that we have some approximate model of how the world works. And with a model, we can then engage in counterfactual reasoning. I can look at what the robot did and ask, well, what might have happened if you changed your behavior, and then use that as a signal to try and judge how effective it was when deployed. So I'd like to set up this problem a little bit more formally as a policy selection problem. Imagine having many of our learning-informed policies to choose from. So we have, let's say, a robot that has 5 different predictive models about what lies in unseen space, and the robot is trying to pick one of those 5 models that will do the best in its current environment. Now, that's very difficult because in different, if I train a model indoors or outdoors, in hospitals or offices, universities, my home, etc., each one of those will then do better or worse when deployed based on the types of environments I find myself deployed in. It's very difficult, though, to determine which of these policies is best because I can only deploy one of these models at a time. So for those of you thinking about this sort of selection problem, bandit algorithms should come to mind, right? You have a sequential decision-making problem where at each time I can deploy one of these models, get a single data point that tells me how well that model did, and then use that in order to try and make better decisions the next time. The problem with this is that this performance is incredibly noisy, very high standard deviation. And so when we're actually thinking about deploying these policies in some upper confidence bound bandit, the classic exploration versus exploitation strategy, the problem is that my performance is so high variance that I converge incredibly slowly. So when we actually deploy these models in relatively simple environments, and I know this looks like a maze, I know it doesn't look like there's any good way to solve it, but we have visual or fiducial features in the image where there are different paths on the ground or different colored wallpapers or different lightings or something that the robot can learn to relate between what it sees and where the goal might be. So it's a very toy-like scenario. But even in these relatively small environments, after 100 trials, the upper confidence bound bandit can't get anywhere near the best performing single policy. And the cumulative regret continues to grow and grow and grow because it hasn't yet converged on which one of these things it thinks is best. Earlier, I mentioned this idea of counterfactual reasoning as being able to help us. And I would argue that this black box model selection approach, that is the hallmark of these upper confidence bound bandit approaches, are problematically slow to converge because they are black box, because I'm not using any of the information I get along the way as the robot navigates to inform my decisions. Instead, I'm really interested in creating like a white box or a clear box approach to these problems. For example, if I were to deploy the robot and get a trajectory that looked like this, you tell me it did pretty well, because it did. The robot found what you know to be the shortest path to the goal. There may be other paths, although technically I close this off. There's only one path to the goal in this environment, and you can see it. Any deviation from this policy would be worse. That's information that you can use already to tell you something about the other policies. And based on our learning of sub-goals planning abstraction, this model-based abstraction that actually tells us how the robot is going to do over time and what it's going to do over time, can help us understand how poorly it might have done had we instead deployed a different model. That's a counterfactual question. How would my performance have changed if I'd gone right at the fork instead? And so we can emulate this, or we can simulate this. We can use the partial map of the environment to create a simulation environment in which we can then deploy other policies that are based on our approach. And based on this, we know not necessarily how badly this other policy would have done, but it is obviously worse. And in fact, this informs a lower bound on the cost associated with this other policy that we can use to constrain exploration for the purposes of bandit algorithm selection. So this process, which after multiple rounds with reviewers, we have settled on calling offline alt policy replay. I'm happy to talk about that adventure, but it was a lot of fun. In retrospect,
hindsight involved.
Hindsight was in there. We call it hindsight replay. That's our hindsight experience replays are our thing. We had like 5 different names before settling on this. This was chosen by committee. It works well enough. But the process works like this. You deploy a robot, and then that partial map becomes one in which you can then deploy any of your other models. Now, again, all of this is only possible really because we have this model for planning under uncertainty. We can put a robot in this situation and using our model ask, what would it have done if placed in the same situation? and based on that, simulate all of these different policies. And just by looking at it, you could probably tell that this pi 3 was the best. Rather than just using this sort of black box bandit algorithm, we can aggregate all of these different computed lower bounds on cost and then combine them to inform better policy selection. And as a result, the next time, rather than picking one of these policies at random, which is what upper confidence bound selection would say that we have to do, we can now pick one that does a much better job at performing well in these domains. And by comparing it against this sort of closed box upper confidence bound solution, you can see that because we're making much better use of the information that the robot collects during deployment, we can converge significantly more quickly to the best performing model, and so our cumulative regret is significantly smaller. So there's a number of different work that we've done in this space. We've also done this during where like domain adaptation is running online. So we have some domain adaptation algorithm running for our predictive model to try and say, oh, the lighting has changed or something during deployment. We're going to try and overcome that. And only when the domain adaptation succeeds at actually mapping the textures between the different environments does our algorithm select it. So when the robot is deployed, it has one performing model like the optimistic model that doesn't do very well, but the learned model is even worse. And the good news here is that as the learned model improves during deployment, it improves and improves and improves. And our, don't call it hindsight, offline all policy replay approach is able to revise old data and ask how would the new model have done and do a much better job of converging quite quickly. So really cool stuff, very excited about all that. It's part of an arm of research in my lab that tries not to just deploy robots that have some learned model that might do well, informed by an abstraction that I'm very happy with, but also to try and use that abstraction to feed back the experience from the robot to introspect and either decide what the best behavior could be, or at least try and police or supervise its behavior while it is deployed in these otherwise unknown environments. So really, really exciting stuff that says we shouldn't just deploy our systems because we hope they work well, but also give them the tools to try and understand how well they're doing. So the final thing that I'd like to talk about is a little off the beaten path, and as a sort of half-forced segue to it, I'd like to mention that so far I've talked mostly about uncertainty in space, the idea that I deploy a robot in an environment where it doesn't know what exists everywhere. It has some ideas of what might exist. It can make predictions about parts of the environment it can't see. But I'm also really interested in this other potential avenue for improvement that I think a lot of people aren't thinking about as much, is that things about the future. Most of the time when we deploy a robot in some sort of cabinet loading scenario, we think about giving the robot an objective, and most task planning or task and motion planning solvers say, complete the objective as quickly as possible. And that's fine. That's a totally reasonable thing to do. But the problem with that sort of scenario here is that when you tell the robot, load all the objects into the cabinet, you get a solution that looks like this. So, all right, so I always ask my students to give me a continuously valued thumbs up or thumbs down. How do we feel about this loading of the cabinet? All right, medium. Yeah, I see medium. Okay, great. That's a good bet, right? Getting confidence is hard, but you get the idea. Did this complete the objective? Yes. But it's not very good. There's something that's unsettling about this organization of the cabinet. You can imagine that the cabinet actually has a top that we removed for the purposes of visualization. But this isn't a very good organization of the cabinet. It succeeded at doing the task, and it actually did it very quickly. But the problem here arises when we start thinking about a sequential task planning or task and motion planning scenario, that when the robot is done with this immediate objective, it then has to do something else. And if the robot is now told to unload the bowls, the problem is that the mugs over here occlude removal of the bowl and must be moved out of the way before the bowl can actually be removed, and then the mugs put back into the cabinet. Solving the task as efficiently as possible over here introduced a side effect on a task the robot hadn't yet been assigned and didn't know it was going to be assigned in advance. The challenge in many domains, not just in task and motion planning, but like task planning in households and homes and other environments in general, is that most robots are problematically myopic, and I would argue seem intrusive and inefficient even when they succeed at doing what they are told. Instead, we have an approach that we refer to as anticipatory planning and anticipatory task and motion planning, which I know some people here are familiar with, which is great, which is this idea that if I were to instead load the cabinet in a more effective way, in air quotes, because I haven't told you what more effective is yet, we can then do a much better job of accessing those bowls and removing all of them. The idea here is that our anticipatory task and motion planning approach uses learning to anticipate and avoid such side effects to improve overall performance for sequential task and motion planning. The idea being that the world does not cease to exist when you are done. I told you that would come back. Is the world does not cease to exist by the time you are done loading the cabinet. You still have to deal with the consequences of your particular choice of solution strategy. And in the spirit of keeping, in keeping with the spirit of a lot of my own, like this other work that I talked about before, I don't think that we should just be replacing planning with learning. I think there's a synergy there that we should try and capture. So really what makes this problem hard is that future tasks are not going to be known in advance. We won't know before we are given them what tasks we have. And so instead, we assume that there exists some implicit task distribution, well, implicit or explicit distribution over tasks in the world, things that you might later be assigned along with how likely you are to be assigned them. And so formally, if you think about this as a one step into the future planning problem, the goal is to find some solution that minimizes jointly the immediate task cost, basically how expensive it is to load all the objects in the cabinet, plus some expected future cost of then accomplishing some other next objective. Again, the expectation is taken with respect to all of the next tasks you may be given and how likely they are. As you can imagine, evaluating this in the wild is very expensive. And so the thing that we do instead is we generate samples of this offline and then train an estimator so that online we can estimate this expected future cost and use it as something like a heuristic to bias plan expansion as we are actually planning during deployment. The way that we have implemented this, at least for now, is this idea that the thing that we're looking to do is run a task and motion planning solver as many times as we can, given the computational budget that we have. And then from there, look at the resulting plans and pick the one that does not merely minimize the immediate cost, but jointly minimizes the sum of the immediate plan cost and the expected future cost as estimated by our estimator. The effect that this has is that the cabinet then becomes more biased towards solutions that aren't just effective as for right now, but also try and make sure to put the world in a state that is then easier to use later on. So this has some, yes, when we return the plan, it minimizes the total cost with this expected value. So the results in these simulated environments show improvements over these many task deployments. And one of the most interesting things I thought was really cool about this was, first of all, this is not cool, this is just the baseline, but the baseline shows that as you load and unload the cabinet, the performance over time doesn't really change very much. You're going to take all the things out of the cabinet, and at some point the robot's going to be told, put everything back in the cabinet. It's just going to do it in whatever structure it thinks is reasonable, right? But the thing here, though, is that when we are biasing our selection of how to organize the cabinet using our expected future cost, using this anticipatory objective, over time, the cabinet becomes more and more organized. As we tell the robot to unload and load things back to the cabinet, it will start to put them in these kind of neat rows that, again, we didn't tell it to do. But this is emergent behavior of thinking like this, that the cabinet becomes easier and easier to use over time. And so the expected value of interacting with the environment becomes lower and lower and lower. Because eventually we are just making the cabinet more and more organized. And I put organized in quotes because I'm defining organized as being the solution to this problem, so it's kind of circular logic. But I hope that at least someone agrees with your sort of common sense like organization that would move your middling, continuously valued thumb to a thumb up. So this is definitely better, and we can also use this expected future cost to prepare the environment in advance by searching over configurations of the cabinet during some downtime between when the robot is giving task, during which the robot would otherwise be idle because it's not given anything explicit to do. The robot can rearrange the cabinet and try and find organizations that are better. By doing this, we find that we actually start in a state that is more organized, that has a lower expected cost to interact with the environment. And when we plan using our approach, we stay there. But as you might expect, if you behave in the absence of our anticipatory objective, the myopic planner progressively makes the cabinet more and more disorganized. So you should find that this is sort of consistent with your, if anybody's ever had a roommate, like in grad school or something, and your roommate just cooks stuff and then never washes anything, your environment looks like this. But if you wash stuff, if you prepare, if you clean along the way, an objective that has nothing to do with the immediate task, but is forward thinking about what you might need to do next, your overall cumulative experience in interacting with the world is made less overall. We show the same thing on our fetch robot. Actually, this fetch robot belongs to Shuisu Zhao, who is a collaborator on this version of the project. We have a number of papers in the space, but this is one of them, where you can see the same behavior on the physical robot. And I love robot demos, but this doesn't add anything particularly new compared to the other things. So, it's nice to have, but also same general idea. But more generally, I really do envision that this anticipation and this anticipatory planning can give rise to many behaviors that we otherwise identify as common sense. But not just saying that we need to learn these things by like imitation, or just saying, here are some rules that enforce that you must load the cabinet in this way, but having these sorts of behaviors emerge based on the robot's understanding of how its actions influence the world. And so I'm really interested in this notion of robots as like long-lived stewards of their environment, that based on an understanding of how their actions now influence both its own future tasks and the behavior of everyone else with whom it shares the world, this can result in many common sense behaviors like tidiness, organization, preparation, unobtrusiveness, and passive assistance. All of these different good behaviors that I think we see and have a difficult time writing down as rules for robots to accomplish in task planning settings in general. So as I wrap up here, I'd like to remind you that, like a lot of this stuff and a lot of my work really is based on this idea that there is an intersection of planning and learning. I really do try to plan using what I know about the world and use planning whenever appropriate, but learning is sometimes necessary in order to fill in the missing pieces, to estimate these statistics of uncertainty for things that you don't otherwise have access to. And in particular, I talked about 3 synergistic research capabilities, going from things like the long horizon task planning under uncertainty, the idea that we can then use these learning-informed models to engage in counterfactual reasoning to try and judge how effectively the learning is informing good behavior, and then finally, this emerging research direction I'm very excited about that I refer to as anticipatory planning. The vision in a lot of my lab is this idea that robots should be performant, that they behave well despite uncertainty in space and time, that they are trustworthy, that they can at least look inward to introspect and judge the effectiveness of their behavior, and are also reliable, according to some definitions of reliable, the idea that planning is sound and complete. And so the robot should still know what types of skills that it can execute and still reliably make progress towards completing its task, despite the fact that the world is not fully known to it. Nearly all of these are challenging because acting well requires imagining the future or some part of the world that the robot cannot see. So my work generally aims to develop these abstractions that jointly afford planning, learning, and introspection. And with that, I'd also like to plug a little bit of our code base. I think we have a lot of like simulation environments. Everything runs in a Docker monorepo. I think we could reproduce 6 papers worth of research in this Docker container from this single repo. I wouldn't recommend it. It takes like 2 weeks to run from start to finish, but we could talk offline if anybody's interested in playing around with some of our code. I'd also like to thank many of my collaborators, both at George Mason University and beyond. I bolded Shwesu because he's an alum here, and I know many of you know him, and my funders, which include the National Science Foundation, the U.S. Air Force, and the U.S. Army Research Lab. And of course, none of this would have been possible had it not been for my students. A lot of this model selection and planning work was done by my student Abhishek. He's on the job market, so if anybody is interested, please do let me know. Send me an email. But other than that, thank you very much for having me, and I'm happy to take any questions that you might have. Yeah.
For the anticipatory planning work, like for the cups and the plates,
Yeah.
I could argue that I could just put that into I could shape my reward function for
Yes.
placement. And I feel like the implication, what you're implying is that it's more correct for me to induce that behavior by thinking about the next task.
Right.
Or a set of next tasks.
Yeah.
But then it feels like we've just shifted that shaping behavior
Right.
off to the task distribution. Now I need a task distribution to make
Right.
that make sense.
Yeah.
So is it better for us? I guess this is just philosophical, but
No,
is
it's
it better
good.
for us to disagree about shaping like a myopic reward, or
Yeah.
is it better for us to disagree about the distribution of future tasks? Or do you think one pushes us closer to truth or something?
I do, and I think mine is closer to truth. And the reason I think that is in part because reward shaping tends to be dimensionless, right? There's this idea of like, if you're just trying to write down a reward, or even like a rule, which is a hard reward, right? That says you have to put these objects in a row. The problem then is to say that if I have a cabinet and I'm only loading 3 of the objects into the cabinet, and you're trying to enforce that the solution obeys those rules, you now need to decide whether or not you rearrange the part of the cabinet that you're not otherwise interacting with in order to complete the objective, while also trying to load those other objects into the bowl. And so when you think not about the reward directly, but you think about the things that you may need to do next, you can know exactly how expensive it's going to be to then take that state of the world and do something else. And so there's like a calibration effort that is more difficult to do if you're just trying to write down these rewards or infer them from imitation. So the task distribution, assuming you can get it, and I'll get to that in a minute, but assuming you have a task distribution, it's a much more natural way of then telling you, here's how difficult it's going to be to interact with the world if I start in this particular state, because that's, I don't know, it's circular logic now because I'm defining the problem to suit my own needs. But I really like this notion of task distribution. And the reason I like it is because any agent that lives in an environment over some moderate amount of time knows their task distribution. Like when you start a new job or something, you're given lots of things to do, and those are samples from your task distribution. There's lots of stuff about how much that evolves over time and stuff like that. And those are maybe other questions about generalization or evolution of your responsibilities. But I think, this idea, and we've gotten some reviewer pushback, I think totally fair about where the task distribution comes from. But sort of like my answer is, if this robot we're going to be living in your house for like a week or two, you give it 100 things to do, that's its task distribution. And I think it's really easy to say that you have the task distribution. If you're planning in the world, you have a model of the world. And then you can just take those two things together and during downtime, simulate all the data that you need specific to that environment to generate this expected future cost and then use it during planning. So there's like a real, I would use a system that was like this, and you don't need to train it directly. It can train itself as long as it has a model of the world. Long-winded, but did that address your question?
I mean, I think so. I just, this is like the domestic dispute in my own household. Is that like, I am very much like, I would put the holes like you put it.
Yeah.
My wife will not.
Yeah.
She's a very intelligent person, so we disagree apparently on something.
Well, what's her task? What's her task distribution?
You're saying I should give her more work.
And
then she'll have to go adapt.
That can't be the
I
answer.
just think it still feels like a choice.
Yeah, right. Yeah, right. Yeah, exactly. Yes. Yeah. I saw another hand. Yeah.
Just picking up on this.
Yeah.
And you've discussed another multi-agent scenario with a graduate student roommate who never washes up.
Right.
So the general question would be, do you have any convergence or equilibrium results involving multiple agents that no knowledge of the strategies of other agents?
No, I'm very interested in this, but so right now, the way that we formulate this problem is very one step, right? In order to try and mitigate a lot of those more long horizon effects that would happen over many, many tasks, we really are thinking only about the next objective, because that is a very straightforward, like supervised learning problem to train. This is not a thing that we're doing. I'm very interested in, but it starts to become really complicated really fast, and I don't have a good answer for you.
I mean, that's a problem that we call ad hoc teamwork in some ways.
Yeah.
We've been looking at that in my group, and some of the people in this room looked at that problem for quite a long time. I just have maybe one question. Also, so many years ago, Todd Hester's PhD thesis was on basically thinking about where never to explore in the world.
Right.
And not where to explore, but where I'm never going to explore. Which sort of has a flavor here a little bit. You're thinking there's both like what tasks are never going to come up and what environments are unlikely. Have you thought about it in those terms at all? Or?
I have actually. So it's more like an armchair way of thinking about the problem is that the thing that we found for most often in this like navigation context or looking for objects, that ruling out certain parts of the environment is indeed the fastest way to make progress most of the time. The problem is that sometimes you're going to have these scenarios where you have like a 20% chance of finding the spare scissors on the desk and you don't remember having left them there or something like that. To just rule out things with some kind of hard rule ends up being a little bit too myopic. So you can get really close to good behavior that way, but it ends up leading to some very, very high cost scenarios where you rule out some of the reasonable solutions and you explore everywhere else in the world to come back to those. And so this more like soft based.
So if you're trying to still be complete, the problem is that in the real world, we can't be complete, right? Like you can't explore everywhere in the world before you die, right? So
absolutely, yeah. So to not totally rule out some scenarios, and I think everything else requires some tunable parameters that ostensibly ours doesn't have. Of course, everything has like neural net architectures you choose and everything like that, but it's meant to address that.
All right. Well, as I said, there is if you saw the announcement for the talk, you also saw the sign up link. There is still some time if you want to meet with Greg in the afternoon. But let's thank him one more time.
Great. Thank you. Great.